When installing parallel conductors, maintaining equal length is crucial for proper current sharing. While achieving perfect equality can be challenging, several steps can minimize length differences and ensure reliable circuit operation. Firstly, meticulous planning of the conduit run is essential. Aim for symmetrical layouts with an equal number of bends and fittings in each parallel conduit. This proactive approach reduces potential length variations from the outset. Secondly, pull all parallel conductors simultaneously. This minimizes any discrepancy introduced by pulling each conductor separately. Starting from one end and working towards the other, feed all conductors into their respective conduits at the same rate. Thirdly, employ a conduit calculator or bending software to determine the precise length of each conduit run, accounting for bends and fittings. This tool provides an accurate assessment of length variations. Fourthly, before pulling the conductors, mark the conduit ends at a consistent point for each conductor. This ensures equal lengths when terminating in the panels. Fifthly, pull the conductors into the conduit until they align with the markings made in the previous step. This ensures that all conductors are pulled to the same length, compensating for minor variations in the conduit runs. While the National Electrical Code, or NEC, does not specify a precise allowance for length differences, industry practice accepts a small degree of variation. A commonly used guideline is the 1% rule, which permits up to 1% difference in length between conductors. In a 300-foot run, this equates to a maximum difference of 3 feet. For critical applications demanding even greater precision, a 0.5% rule is sometimes applied. This allows for a maximum length difference of 0.5% or 1.5 feet in a 300-foot run. A small length difference between parallel conductors has a minimal impact on current division. This is because the impedance of the conductors is very low. Current tends to flow along the path of least resistance, and the slight impedance variation due to length difference is usually insignificant. The impact of conductor length on current division can be explained by considering the impedance of each parallel path. The impedance, denoted as Z, is composed of resistance, R, and reactance, X, where Z equals the square root of the sum of R squared and X squared. For conductors in alternating current, or AC, circuits, the reactance is mainly inductive reactance, denoted as X sub L, and is equal to 2 times pi times the frequency F times the inductance L, that is, X sub L equals 2 times pi times F times L. The current in each parallel conductor can be approximated by the formula I equals voltage V divided by the impedance C. Therefore, if one conductor is slightly longer than the other, its impedance will be slightly higher. However, the difference in impedance is usually very small compared to the overall impedance of the circuit. The small length difference of conductors also affects the voltage drop. The voltage drop across each parallel conductor can be calculated using the formula voltage drop equals current I times impedance C. If one conductor is slightly longer, it will have a slightly higher impedance, leading to a slightly larger voltage drop across that conductor. However, similar to the current division, the impact on the overall voltage drop is minimal when the length difference is kept within acceptable limits. To ensure proper installation, consider the following additional factors. Firstly, use the same type, size, and insulation for all parallel conductors. This ensures uniformity in their electrical properties. Secondly, terminate all parallel conductors in the same manner. Use properly sized connectors and ensure tight connections to minimize resistance. Thirdly, space the parallel conductors evenly to promote equal heat dissipation. Avoid bundling them tightly together, which can lead to overheating. The length of the equipment grounding conductor, or EG, for parallel run should also be considered to ensure it is adequate for fault current carrying capability. The EGC should be run in parallel with the circuit conductors and sized according to NEC Table 250.122. The length of the EGC should be as close as possible to the length of the phase conductors to minimize impedance and ensure effective grounding. When dealing with parallel conductors, several other considerations come into play, including ampacity adjustments and conductor bundling. Ampacity refers to the current carrying capacity of a conductor. The NEC provides tables that specify the ampacity of different conductor sizes based on their insulation type and ambient temperature. When conductors are installed in parallel, the ampacity must be adjusted to account for factors such as the number of conductors in a raceway or cable and the ambient temperature. These adjustments are necessary to prevent overheating and ensure the safe operation of the electrical system. NEC Section 310.15 addresses ampacity correction and adjustment factors. When multiple current-carrying conductors are bundled together in a raceway, cable, or directly buried, the heat generated by each conductor can raise the overall temperature of the conductors. This increased temperature reduces the ampacity of each conductor. To account for this effect, the NEC requires that the ampacity of the conductors be adjusted based on the number of current-carrying conductors in the bundle. The adjustment factors are provided in NEC Table 310.15 colon. Ambient temperature also affects the ampacity of conductors. The ampacity values listed in the NEC tables are based on the specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this value, the ampacity of the conductors must be reduced. The correction factors for ambient temperature are provided in NEC Table 310.15 bone. In addition to ampacity adjustments, conductor bundling can also affect the impedance of the parallel conductors. When conductors are bundled together, the proximity effect can increase the AC resistance of the conductors. This effect is more pronounced at higher frequencies and with larger conductor sizes. The increased AC resistance can lead to increased voltage drop and losses in the electrical system. To minimize the proximity effect, it is recommended to space the parallel conductors as much as possible and to use non-ferrous raceways. The skin effect is another phenomenon that affects the impedance of conductors at higher frequencies. The skin effect causes the current to concentrate near the surface of the conductor, reducing the effective cross-sectional area for current flow. This increases the AC resistance of the conductor and can lead to increased voltage drop and losses. To minimize the skin effect, it is recommended to use larger conductor sizes or to use conductors with a larger surface area, such as hollow conductors or conductors with multiple strands. Another important aspect of working with parallel conductors is ensuring proper coordination of overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When conductors are installed in parallel, the overcurrent protection devices must be coordinated to ensure that they operate correctly and provide adequate protection. The NEC provides specific requirements for the selection and coordination of overcurrent protection devices for parallel conductors. NEC Section 240.4 addresses the protection of conductors, and NEC Section 240.20 addresses the rating of overcurrent protection devices. When selecting overcurrent protection devices for parallel conductors, it is important to consider the ampacity of the conductors, the inrush current of the load, and the interrupting rating of the overcurrent protection device. The overcurrent protection device must be rated to protect the conductors from overloads and short circuits, but it must also be able to withstand the inrush current of the load without nuisance tripping. The interrupting rating of the overcurrent protection device must be sufficient to safely interrupt the maximum available fault current at the point of installation. In addition to selecting the correct overcurrent protection devices, it is also important to coordinate the overcurrent protection devices to ensure that they operate in the correct sequence. Coordination is the process of selecting and setting overcurrent protection devices so that the device closest to the fault will trip first, minimizing the extent of the outage. Coordination can be achieved by using time current curves, which show the tripping characteristics of the overcurrent protection devices. By comparing the time current curves of the different overcurrent protection devices in the circuit, it is possible to determine whether they are properly coordinated. It is also crucial to consider voltage drop calculations for parallel conductors to maintain adequate voltage levels at the load. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and that the total voltage drop from the source to the furthest point in the circuit should not exceed 5%. When conductors are installed in parallel, the voltage drop is reduced because the current is divided among the parallel conductors. However, it is still important to calculate the voltage drop to ensure that it is within acceptable limits. The voltage drop can be calculated using the formula voltage drop equals current I times impedance C times the length of the conductor. When calculating the voltage drop for parallel conductors, the current should be divided by the number of parallel conductors. The impedance of the conductor can be obtained from the NEC tables or from the conductor manufacturer. The length of the conductor should be the actual length of the conductor run. Another important aspect of working with parallel conductors is the selection of appropriate connectors and terminations. Connectors and terminations are used to connect the parallel conductors to each other and to the equipment. The connectors and terminations must be properly sized and installed to ensure reliable and safe electrical connection. The NEC provides specific requirements for the selection and installation of connectors and terminations. NEC Section 110.3 addresses the examination, identification, installation, and use of equipment, and NEC Section 314.16 addresses the number of conductors and outlet device, and junction boxes, and conduit bodies. When selecting connectors and terminations for parallel conductors, it is important to consider the conductor size, the conductor material, and the environmental conditions. The connectors and terminations must be rated for the conductor size and material. They must also be suitable for the environmental conditions such as temperature and humidity. The connectors and terminations must be installed according to the manufacturer's instructions to ensure a proper connection. It is also important to torque the connectors and terminations to the specified torque value. The torque value is typically provided by the manufacturer. Over-tightening or under-tightening the connectors and terminations can lead to a loose connection, which can cause overheating and failure. Proper grounding and bonding are also essential for parallel conductor installations to ensure electrical safety. Grounding and bonding are used to provide a low impedance path for fault current to flow back to the source. This helps to protect people from electric shock and to prevent equipment damage. The NEC provides specific requirements for grounding and bonding. NEC Article 250 addresses grounding and bonding. When conductors are installed in parallel, the grounding and bonding system must be designed to handle the increased fault current. The size of the grounding and bonding conductors must be increased to accommodate the increased fault current. The grounding and bonding conductors must be connected to a common grounding electrode system. The grounding electrode system must be properly installed and maintained to ensure a reliable ground connection. In addition to the above considerations, it is also important to follow all applicable codes and standards when working with parallel conductors. The NEC is the primary code that governs electrical installations in the United States. However, there may also be local codes and standards that apply. It is important to be familiar with all applicable codes and standards before starting any electrical work. It is also important to obtain the necessary permits and inspections before starting any electrical work. Permits and inspections help to ensure that the electrical work is performed safely and according to code. Working with parallel conductors requires careful planning, execution, and attention to detail. By following the best practices and guidelines outlined above, it is possible to minimize length differences, ensure proper current division, and create a safe and reliable electrical system. The 1% or 0.5% rules provide reasonable benchmarks for achieving negligible impact on circuit operation. To summarize, firstly, plan for equal length by using the same number of bends and fittings. Secondly, pull wires simultaneously to minimize differences. Thirdly, utilize a conduit calculator to determine the exact length. Fourthly, mark conduit ends to ensure equal length. Fifthly, pull to markings. A length difference of 1% or 0.5% is generally considered acceptable.